and gentlemen, and thank you for the kind introduction. This is Daiji Fukuda from National Institute of Advanced Science and Technology, where I serve as a prime senior researcher. So it is a great honor to be able to present at Q2B23. Thank you very much for the opportunity, and I'd like to express my gratitude to the organizers. I know it will be a tough job to organize all of that, but we appreciate your efforts. So today I'd like to discuss the quantum optical sensing and metrology for quantum optics at our institute, which is called AIST. We are using semiconducting to use single photon detection, and we are involved in research and development as well as application, and we are also developing a test bed. We are also trying to make sure that the metrology is right so as to help develop the use of quantum technologies and quantum sensing in particular. Actually, this morning in the governing session, my colleague, Dr. Horibe, made a presentation. And this is a little duplicative of that. So our institute is to establish a new organization by the end of this month. It is titled Global Research and Development Hub for Business by Quantum AI Technology, or GQuat for short. And so we will provide a location for research and development of quantum devices and provide prototyping services, and we intend to become the international hub for industrial applications of quantum technologies. So we have the fabrication facility, we have the clean room for superconducting, we will also have a design fab for superconduction and silicons, and allow for large system quantum devices to be built there. And so that will lead to new quantum devices, and that could be combined or used in tandem with computers, both quantum computers and AI as well, so that it can be brought to use for logistics, drug discovery, material design, communication, energy, among others. And so we are actually looking at various use cases. We hope that there will be new use cases that no one will imagine today. So if any of you are interested or you have any ideas, please come to me or my colleagues, and we will be delighted to discuss all of that. So basically, we are working using the quantum annealers and quantum computers. That would be the first quantum devices to come. But we are also focusing on optics using light, and I'm the optics guy. So I'd like to particularly talk about activities in that regard. So first, our strategy at AIST for development of quantum sensing. As you can see, these are the three pillars of our R&D. One is the core technology, and then we have application and test bed, and the third pillar is metrology. So the core technology is about quantum optical sensing, what specific technology to develop. And when it comes to quantum sensing, as Dr. Tatano discussed, you could use diamonds, but we are particularly focusing on light and optics and really precision measurement of those photons. So non-classical and quantum states, we want to measure that, which means that the classical measurement instruments are no longer relevant. We really need very high performance. For example, the detection efficiency, we would need near 100%. And so we will need very high speed, and we also need to be able to detect photons. As of now, what technologies are out there? We only have one solution, which is using superconduction. But then superconduction is usually associated with cryogenic cooling, and that will need some expertise, and you will need the cryogenic coolers, which are expensive. But if we are to focus on the optical quantum sensing, we want it to be easily or readily usable, but currently we have a high threshold, and we believe AIST can actually serve a role there to lower that barrier or entry barrier. So we are trying to look at development and fabrication of the sensors. And we also want to present what applications are possible and host a gathering of interested people so that the quantum-based technologies are more readily usable widely. And for those quantum devices to be used widely on a business scale, there will be various components and performance requirements. And the question would be how to ensure that the performance is what it claims to be. And at that stage, metrology will become relevant. For example, if you have the encoded communication, encrypted communication, you would need to know the number of photons to begin with. Otherwise, you won't be able to ensure security of that communication. So the amount of light, meaning the photon count, needs to be measured, and that requires a very high level and sophisticated level of metrology so that the use of quantum optics can develop in a healthy and steady manner. So I'd like to refer to some cases. So first, quantum optical sensing. At this point in time, let's look at what optical computing uses. We have some results of some groups within AIST, and I'm just showing part of that. So they can be largely classified into Gaussian boson sampling and fault-tolerant quantum computer with photonics. So with regard to boson sampling, Canada's Xanadu and Chinese SES are among the leading players there in that field. And so this is one part of quantum computing, and it is really geared to a particular type of computing, such as a combination, etc. And they are capable of solving those particular questions at very high speed. And we understand that at 50 quantum number of 50, they have already demonstrated their effectiveness. On the other hand, the fault-tolerant quantum computer with photonics, this is quite challenging. We don't really have a real system available yet, but there are some players, as you can see on the slide, and various ideas are coming out. So what's common among those architecture is here in the lower half. So we have some quantum light source, and we will create this state and then put it into a programmable state, and then you will get an output and detect that, and that would be the result of the computation. And in that process, the issue is because light is a boson, the quantum state is overlapped, and so we will need to understand the number of photons that will define the quantum state. And so determining that is a big challenge. So ordinary detectors like APD for semiconductors, you can't actually count the number of photons. And so for these computers or for good boson sampling, one big challenge is to have a very high performance photon detector. So what we are doing here is we are using superconduction. And I'm sure anyone here would understand what superconduction is. And so it's about metal resistance dropping to 0 ohm at a certain critical temperature. So there's this drastic transition happening, and we are using this transition to detect the photons. So we're using the transition, and so that's why we call this TES, the transition edge sensor. So the TES depends on the incident energy of the photons. And so this is what we've developed at AIST. It's a photograph. So each block is a sensor, and we have the optical fibers connecting them. So the important thing is about the incident photon state and how you can detect that very faithfully. And you mean that the loss needs to be small or the detection efficiency needs to be very high. And to realize that, we are using a particular optic cavity so that the light can be absorbed as much as possible. Or here we're looking at this high efficiency connection of optic fibers. And so now we have actually realized a detection efficiency of above 98%. So here we have the coherent light and we measurement of that. So with a coherent light, they are discretized and you can see what the waveforms look like and you can see the discrete levels. And so for each wave height, the distribution is shown in the lower part, which actually reflects the quantum state. And so the height of the signal can actually directly convert it into the number of photons. So we have these unique features of this photon detectors. And I'd like to talk about two cases of application. One is about using the quantum information. So we talked about this photonic quantum computer, and that can use this technology. And to realize that, one important thing is this. For any calculation, we will need to have 4 linear transformations and 1 nonlinear transformation, those 5 in total. This is known. So those are phase shift, displacement, squeezing, beam splitting. Those are the 4 linear transformations. And then squeezing needs somewhat more of technological development, but those 4 are already available in one form or another. So those are very ready for optical computers. But the challenge is really the nonlinear part, which is called the CPG, the cubic phase gate. And this needs to be realized and for a real photonic computer. So we have 2 qubits, but you have a great. But then in the case of light, the coherent time is long, but each photon has very small nonlinear part, and therefore the CPG is very difficult to develop, and we want to resolve that challenge. And so for the cubic phase gate, there are a number of protocols that are already proposed, and we are thinking about a special state which is very non-classical, and we are cooperating with University of Tokyo and NTT to develop that. And so this shows what we are doing. So NTT has a very high pressure, high quality crystals that we can use, and then we will use that and send it to our photon detectors for detection, and then we will use a homodyne detector to measure the generated states. So here, suppose you subtract n photons, that will mean the remainder is less 9 photons, and so we will need to look at what happens after that those n photons are subtracted, and this is what you get. So the upper part is the experiments, and n is the number of subtracted photons, and the bottom part, bottom panel shows simulations. So n equals 0 is the same, so the squeezed light comes out as is, and you can see there's a kind of ellipse also. And so according to the Heisenberg's uncertainty principle, that's a little squeezed, and so some noise on this direction and less noise in this direction. But the point is, at any cross section, it is a Gaussian distribution, so it's only linear operation that's you can do. So that's the limitation as long as you're using squeezed light. But then if we have 1 photon subtracted, you can see there's more distribution on both sides. And if you look at the cross section, this is non-Gaussian. And so we can use a non-Gaussian state. And so this is like the Schrödinger's cat situation. And so this is very non-classical. Further, in the middle here, we see this dent, and we have this negative figure. And the negative figure is not possible according to classical physics. So, this is like the probability going into negative territory. So it shows how nonlinear we are getting. And then this is actually without loss correction. And so this is actually the first of its kind in the world. And so we are really working hard so that we can realize this cubic phase gate and further on go to developing a real quantum computer. Now the second case, and this is about applications for life sciences. And so on a totally different tone. So we have some dyed cells, and we apply some laser light. Then there will be very weak fluorescence coming out. And the wavelengths can tell us about what reactions are happening inside the cells or what functions are related to that particular part. And so this is about getting to know more about what's happening inside the cells, and that should lead to important understandings about the mechanism of life. And so we're trying to use this technology. So here we have this cell from the vein of a cow. And so blue is a nuclear, and then we have the mitochondrial, etc. So different colors indicate different parts. And so this is just one example, successful one. The important point is that we're only using a very weak power of 1 microwatt. Usually 100 microwatt or that level of power was necessary, but because of quantum sensing, we can actually use a much weaker light to get the same information. So, if you have cells in a colony, and suppose you have some normal cells, but some aberrant cells as well, or maybe one cell is actually producing an industrially usable and useful material, but others are not, it may lead to us being able to discern that very easily and clearly. So the thing is, we can actually, or we may be able to observe those cells in situ, and we're working with Tsukuba University under a consortium to develop this line of application. And again, this is really about bringing quantum sensing to everyone. Final topic is about metrology. So this is really creating or providing the foundation of the use of quantum optics and quantum devices. And so we are trying to provide a standard or reference for a single photon radiometry. And so this is really about developing a national standard for traceable performance testing of optical devices, so that we can have reliable detection efficiency devices becoming available for people. And obviously, if there's a company developing and marketing that, that can actually be a seal of approval. We are also trying to provide reliable detection efficiency evaluation. Various components would be necessary, and each and every one of those components need to be evaluated in a reliable way. That's the same for everything. So it's about any optical or quantum device, and make sure that the performance standards are there. So QEDC, EMNQ, there are a number of gatherings that are working on that, and AIST is working with those initiatives. And we are also trying to make sure that the measurement validation is happening and there is harmonization across the borders. And so we are referring to the international developments and making sure that there is an international standard so that the certification is valid anywhere on this planet. So that was about the three activities at AIST, the National Institute of Advanced Science and Technology. Thank you very much.